basically take different terms and show you how we can build up. Now finally we will today solve these equations, and whatever necessary information is needed, that we have means background is needed for solving Navier-Stokes equation, that is already covered. Okay, so today's class will be all about to solve Navier-Stokes equation, and we will see that thing. Okay, so let us begin with that. I once again, let me bring the slide on the screen. And let me make it full screen. Yes, so I think you can see it. Please confirm me. You can see the full slide, right?
Yes.
Okay, good. So you see, this is again I am going back to the contents. We started with the lecture of introduction to CFD in the first one. Then in the second lecture we covered idea about governing equations and different discretization methods like finite volume method, finite difference method, etc. How to solve linear equations. So those things we have discussed little bit. Then finite volume method of one-dimensional heat conduction and convection equation. So this we tried to solve. One class we have spent to introduce the ANSYS fluid with the help of some examples and case studies, and I asked you to practice some of them. Then in the last class we were discussing the unsteady state conduction equation, heat conduction equation. Objective is to make you clear that how the unsteady term, that is the temporal derivative, can be discretized with the help of Frank-Nicolson, explicit, implicit method, etc. That was the agenda of last class. We also have seen that whenever some interpolation is needed in case of finite volume, etc., from cell center to face, then some interpolation schemes are needed, like first order upwind, second order upwind, central differencing, power law scheme, quick scheme. So that thing very brief we have described. Now today we will come to this most important part, pressure velocity coupling. That is all about the solution of Navier-Stokes equation. Okay, so let us cover these things, and all of you be attentive, because this is if you understand this concept, then main thing is covered. Okay, so it will be very good. So I have given the title of this talk, today's lecture, like this: solution of incompressible fluid flow equation. So far we were interested in heat transfer equations for the simplicity. We started with simple steady state conduction equation, then unsteady state conduction equation. Now today we will go to the fluid flow equation, and for simplicity we will consider only incompressible flow. But if you understand this incompressible flow, that compressible flow will be just a different version of it. Okay, so let us consider incompressible fluid flow equation, and for this case, for incompressible fluid flow, if we look into the governing equations, so in 2D, so these are the things. So this is Navier-Stokes equation. So you know that this is temporal term, these two are convective term, okay, and this is your diffusive term, and this is pressure head. So if you recall, we first wanted to discretize this domain, this conduction equation or diffusive domain, diffusive part, okay, in the form of one-dimensional steady state heat conduction equation. So we have seen that there are so many discretization techniques, either finite volume or finite difference. Again, in finite difference we can have forward difference, backward difference, central difference, etc., and this part can be discretized. Then we invoke the unsteady state term, this one. So here we have seen we have Euler method or explicit method, or Frank-Nicolson method or implicit method. And whenever you are bringing this temporal term and diffusive term together, you need to take you need to take some stability criteria. Okay, so there are so many stability criteria there: TFL stability criteria, von Neumann stability criteria. I have not gone to those details, but you know that whenever delta t and delta x both will come into picture, it has some relations. Okay, so we told you that r should be less than equal to 0.5. That is one of the criteria. So in that form, you need to choose it. Then we took a species transport equation in the last class, where we have shown that using finite volume method approach, how these two equations can be handled, because you have to leave, these are nonlinear terms. Why nonlinear? Because coefficient of this term, you see this coefficient rho u is also a function of u. Okay, so if this is function of u, then means u means the variable which you are taking derivative here, del u del x. So then this becomes a non-linear term. Now we need to linearize it by doing consecutive 2 rounds of integration. Okay, so that we have seen in the last class. So everything is step by step covered. Only the remaining part is this del p del x. Okay, so that will be extra term which is coming here in case of fluid flow. Pressure is coming into picture. The discretization of it is not a problem, because this is a spatial discretization. You can either use central difference or forward difference, backward difference, etc., and you can discretize it. So all the terms, if you discretize using proper scheme, then this differential equation will give you a linear algebraic equation. Okay, then you need to solve. So this is x component and this is y component, and you know that these two have three unknowns. If you consider this 2D problem also, you have all unknown u, v that you have to solve. In addition, you need a pressure term, because this u and this velocity and pressures are related. Okay, so your velocity will be guided by the pressure difference, by the pressure of the term. Okay, so these relations are there. So you need, since three unknowns are there, you need an extra equation which we get from this continuity equation. Although we do not solve this continuity equation directly, we try to convert it in the form of an equation called pressure correction equation. Okay, so that we will see that how this pressure correction equation can be developed, and how these pressure correction equations can be coupled with these things, so that we can do this pressure and velocity coupling. Okay, so this is an important part that we will try to understand today. So that is an important thing. Okay, so this is all about 2D Navier-Stokes equation. Now if I go to the 3D Navier-Stokes equation, the term is almost same, that this is only one extra term will come. This is continuity equation, this is x term, y and z term. So you see here temporal term, these three are actually convective term, this is pressure term, and this is your diffusive term. Here in both these cases, you cannot see the body force term. Body force means ideally you should have a rho g, right? Rho g means gravitational force or any other force term that should be there. But conventionally, this pressure that we are writing here, this pressure can be this gravity or extra force term can be incorporated in this pressure. Okay, so this pressure, whatever you are seeing, is basically normal pressure plus you can, that gravitational force can be added here. Rho gh, sorry, rho gh can be added here, and this is then called piezometric pressure. Okay, so piezometric pressure actually encompasses both the normal hydrostatic means hydrodynamic pressure, and as well as the body force can be coupled with it. The reason is simple, you just like to simplify the equation. Okay, so this pressure actually contains both the normal pressure and your gravitational component. So that's why we are not writing the gravitational force or body force separately. So we are clubbing it into this. So in the second equation also the same case, and this is a standard practice, that you write the P including the gravitational part. Okay, so this is x component, this is y component, this is z component. These three things are there. So we will first try to see that how two-dimensional equations can be solved. So three-dimensional will be only just an extension of it. Okay. So the moment the matter of solving Navier-Stokes equation, two major difficulty arises. Okay, which is shown here. first of all, one is that is non-linearity. Non-linearity means what? So you have some non-linear term here. Okay, so these terms are non-linear. Okay, as I pointed out. So this non-linearity will pose some complexity that this as you can see, I am quoting some text here that the convection coefficient rho u is a function of the dependent variable u. However, this can be treated like a conductivity k being a function of temperature T as discussed in earlier chapter. So starting with a gauged velocity field, so how to deal with this non-linearity? So you start with a gauged value of pressure, gauged value of velocity, and then you try to correlate it with the pressure correction term. Okay, so that's how you can manage it. So in terms of non-linearity, this is basically a matter of more complex, more computation time, but it can be managed. So non-linearity, although is a problem, but it can be handled. You need to go few more steps. But major problem arises with this pressure gradient part, because this pressure and velocity P and V are correlated. Okay, so if this extra calculation of pressure is main problem. So if there is a fluid domain, let's say this is a domain where we are like to solve the equation. Okay, so if at all the points my pressure is defined, then solving Navier-Stokes equation is not a big deal. Okay, so if pressure field is known to you, but if most of the time this is not given, okay, so if pressure field is not given, then you need to evaluate both velocity and pressure simultaneously. So you will be given only with the inlet boundary conditions, and from this inlet boundary condition you need to proceed in this direction. If the flow direction is in this positive x direction, then at each cell you need to calculate both pressure and velocity simultaneously in a coupled manner. Okay, so this part makes the process more complex, which was not the case in heat transfer equation. Heat transfer do not require any pressure field, because the equation do not contain any pressure. But in case of fluid flow, it is the pressure comes, and that's why this makes the process little complex. Okay. So how to solve it? How to approach towards this problem? So one of the most popular methods. So there are many methods for doing this pressure velocity coupling. Okay. So one of the very popular and almost very old method is called a simple method. Simple method, it's not like it is easy. For simple means it is easy. So it is comes from the short form. It is semi-implicit method for pressure linked equations. Okay, so this is the short form becomes simple. Okay, so semi-implicit method for pressure linked equations. So this is a method, so that we will study. There, although it was proposed and it was widely accepted, then little bit of variation like simplex, simpler. So different methods was reported later on, but this is old and this is even applicable in today. So those who have experience in running and fluent etc., you will see that when you are giving the solver option, then you will get this particular part. Okay, so this simple part. So this understanding is needed. So let us try to understand step by step that how this will be moving. So basic the basic method is what? So basic method is basically a cyclic series of guess and correct operations. Means you first take a guess value and then try to correct it. So what happens? So again, let me draw a domain, a computational domain where we are interested to solve the fluid flow. So let's say this is the domain. Okay, so what we will do, we will first guess some value. So these are the, if I consider finite volume or finite difference, these are the points. So at these points we will we have to assume some value, pressure, velocity, etc. So that comes from the initialization step. So in software you will see there will be a step called initialization. That means you have to assume some value of u, v, w or pressure at this point. So that is the initialization step, and then initialize, and then you see that whether this, let's say if I consider u and v at a particular cell, then we need to see whether it satisfies the pressure equation or continuity equation or not. If it do not match, then we will try to correct it in a step by step manner. So it's basically a guess and correct operations to solve the governing equation. So, so what it states that velocity components are first calculated from the momentum equation using a guessed pressure field. So a pressure field is guessed first. The pressure and velocities are then corrected to satisfy the continuity equation. So what happens? You first guess a pressure field, and based on that you calculate the velocity. Now definitely the velocity, since you have taken the pressure field a guessed value, the velocity will not be correct. So it will not satisfy continuity equation. So if it do not satisfy, then you try to correct it. Okay, so take some other value. So like that way, in each step you need to match this. So until and unless your, so when your calculated velocity will satisfy continuity equation, that means that the gauge pressure value field is correct. Okay, so that's how things will move on. So this is the basic approach. Now to understand this, we need to before going to the detailed steps of simple, we need to understand another important concept which I given little hint in the last class, that is called staggered grid, its implications. Okay, it was proposed by Welch in 1965, and who also developed another method called MAC, marker and cell. So MAC is another method like simple. Okay, so Welch proposed that thing, and then it states that the location of the velocity components u and v placed at the faces of the control volume and staggered with respect to the pressure and temperature. Okay, so this is the proposition. Let us we'll understand it step by step manner. So first, let us consider a simple one-dimensional equation, a steady state equation like this. Okay, so this is a momentum, steady state momentum equation. So temporal part is not there, only convective part is there, diffusive part is there, and pressure part is there. Just to simplify it and to understand the staggered concept of staggered grid. So let us consider it, and what we generally if we do not means our approach, whatever we have discussed. So if you think of that, so let us consider, if we consider control volume approach. So all these are control volume, and the values are generally stored at the center. Okay, so these are the center, these points are center, and these lines are basically face of a particular control volume. Okay, so ideally what we know that we will store the values at the center. So for that, for example, for this particular volume element, this at the center we will store u, v, and w. Okay, so that is how the standard method goes on, but there is some problem. So if we follow the standard part, then there will be some problem. For example, if we discretize this equation, this one-dimensional equation that we are considering, you see that this term, this convective term, if you discretize, we can write it in this way. Okay, rho at any ith cell, rho I ui plus 1 minus ui minus 1 by 2 delta x. So this is using central difference scheme, and then this diffusive part equation is discretized again in central difference scheme in this way, and this pressure term is also discretized in this way. Okay, so in this finite difference method, we can simply convert this differential equation to this kind of algebraic equation. So this is the standard case, right? Now what are the limitations for doing this? You see that this pressure term, when we are discretizing it, basically taking the value of pi plus 1 and pi plus I minus 1, and not considering any value of pi. Okay, so although you are writing this equation for ith cell, so again let me draw it. If I consider, one cell, let's say this is the ith cell. Okay, so this ith cell, if I am writing, so you see that this is I, so your I minus 1 will be this one, your I plus 1 will be this one. So you are considering pressure at this pi minus 1, this point, and this point for calculation of the properties of this point. Okay, so you will calculate ui here, but you are considering pressure at this point and this point. So your pressure of the alternative points are not having any influence on the velocity at ui. So this at I value, the velocity ui is not having any effect of pressure, because your pi is defined one step ahead and one step after, right? So this creates a problem. So these implications, if I show you see the pressure is taken from a coarser grid than the one actually employed. This would reduce the accuracy of the solution. So this is the first problem. First problem is what? You see that although your velocities are going cell wise, one by one cell, with if this is delta x, then at delta x direction, your pressures are being discretized at a 2 delta x of them. So pressure is being calculated at a coarser grid, and if the grid is coarse, it has some impact. So I told you that grid size, the smaller it will be, your truncation error will be lesser. So that is one problem, but even more problem will arise if you consider a situation like this. So for a case, for example, if you have a wavy pressure field, let's say you have a wavy pressure field, means these are the grid points. So at one grid point you have value of pressure 100, and you have here 100 alternative points, and another point 300, and then there these are 300. Okay, so basically this is a wavy pattern. Okay, so if you consider, so this will be having 300, again 300, so this is a wavy pressure distribution, is wavy in nature. But this discretization scheme is considering the alternative point. That means what? For calculation of this point also, it is taking the values of this one, this 100 and 100, right? Again an alternative point 100. So in this kind, although this pressure field is wavy, your this discretization will show that at all the points pressures are 100 only. So it will show only a 100 pressure field. So that uniform pressure field it will be reflected. And you know that OAB pressure field is not a very uncommon. In many applications, some non-homogeneous pressure field is highly available, means highly encountered. So even the pressure field is varying, it has a varying nature, but this particular discretization or arrangement will show you that it is uniform. This is a major limitation. So you cannot track the exact nature of the field due to this kind of discretization, because you have assigned all the values at the center. Similarly, that similar problem will happen in case of continuity equation. So continuity equation is what? du dx plus du dx plus dv dy du dy equal to 0. This is for 2D. So if I consider one dimension, this will go to 0. So only this will stand, du dx equal to 0. So again, using central difference scheme, because we prefer central difference because it is more accurate. So ui plus 1 minus ui minus 1 by 2 delta x will be equal to 0, right? So this means that it states that ui plus 1 and ui minus 1 will be equal. So at each alternative points, if this is your grid point, okay, so this is I plus 1, this is I minus 1, like that. So you see that it states that this point and this point are same. Again, the alternative point are same. Now this may be the possibility, there may be the possibility that again you can encounter a wave pressure velocity field. Okay, so wave velocity field means there is possibility that at this point 100 velocity is there, at this point 500, again 100, 500. So these kind of values are not very uncommon. Okay, so inhomogeneous pressure velocity field can be possible, but due to this arrangement, due to this gridding arrangement, you will see that these alternative points are all having 100. So that means after discretization you will get a uniform velocity field. Okay, so you cannot track this kind of variation. And another limitation is obviously there, that your grid size, you are taking I plus 1 and I minus 1, not considering the I part for the careful discretization at I. So that is that means that you are taking a larger size of grid. Okay, so that will have another set of error. So these kind of limitations will come. So now how we can solve it? So what are the remedy? So remedy is a staggered grid arrangement. Okay, so let me first explain it here, that how, what do you mean by staggered grid. So these are control volumes. Okay, so in these control volumes, the center of the control center point is denoted by cross, where actually we will save the pressure, or if you solve the energy equation, then you store temperature, or if you have any other properties that you all you store at the center. Okay, and the velocities are declared at the cell faces. So these are the cell center and these are the face, that we have explained in the last class, that how the control volume, control phase, etc. are declared. So these lines are basically phase, and this center is the cell center. So you store at the cell center, the cross mark indicate the storing position of the pressure, and the point of the face means this one, for example, here in this vertical line, you just store the u velocity. Okay, so where it is stored, that the midpoint of the face, so it is indicated by the circle. So this circle is storing the u velocity, and where the v will be saved, so v will be here. Okay, so this is for 2D, uv both will be there, and if w is there, so that can be another direction which is upward to this plane, so that again can be stored there. So you see that velocities are saved here and pressure is calculated at the center. So this is why it can form a staggered arrangement, that for ith cell, let's say if this cell is I, so ui will be here, here will be ui, here will be vi, and pi will be stored at this position. So the advantage is that the moment you are now calculating the velocity, you will consider the pressure field of this point and this point. Okay, so instead of alternate points, so you will take a pi plus half position value you will get. So your pressure value of this point and this point will be reflected at this u position. Okay, so the intermediate u will be automatically corrected during this arrangement. Okay, so this is called staggered grid, and this has some advantage. Okay, so advantage of that kind of OAV pressure field, or you need not worry about that larger grid size that was coming into picture. So those type things will not be here. Okay, so that's why we prefer this staggered grid arrangement. So its advantage is like this, that for a typical control volume, as shown there, the discretized continuity equation would contain the differences of adjacent velocity points. Hence, a wavy velocity field would not be satisfied. The pressure difference between the successive grid points now becomes natural driving force for the velocity component located between the grid points. So now in this kind of arrangement, you will see that when we will write that this u velocity will be determined by the pressure at this point and this point, these two consecutive points, rather than these alternative points. Okay, so this has the advantage, and that is why, although it poses some coding complexity, or your programming needs will be a little complex, but its advantage is much more. That's why this is accepted. And the simple algorithm that we are going to learn now, that will be based on this staggered grid arrangement, where your velocity will be placed at the cell face, and pressure will be stored at the cell center. Okay, now let us move to this simple algorithm. Just 1 minute. Okay, so this is all about the simple algorithm. So first I will try to explain the science behind it, means the theory behind it, then we will go to the steps. So this is our equation, right? This is our two-dimensional x component of the Navier-Stokes equation. So we have u and p, these two are unknown for this particular case. So for this x component, similarly for y component there will be v and p, these two are unknown. So note it, in this procedure the actual pressure p is written as this one, p equals to p0 plus p dot. So note this very carefully, p0 plus p dot, where this p0 is the estimated or intermediate value of the pressure. So p0 is the estimated value and p dot is the pressure correction. So in the estimated value means you need some, you are taking some gauge value, etc. And if you add the correction term, then you will get the exact pressure, that is that satisfy the equation. Similarly, we will consider that the velocity u component is or can be expressed also u0 plus u dot, where u0 is the estimated velocity and your u dot is the correction term. Okay, because estimation cannot be correct, estimate is an estimate, you have to correct it based on the equation. So if you add this correction term, then you can satisfy this u, which will be valid here. So this is how we are defining the pressure velocity. Now we will substitute this substituting u0, v0 and p0 for u, v, p in the x momentum equation. So in this x momentum equation where we have u and p, and for y component we will also get v. So we will just put those values there, put u0 there, that estimated values there. So we will get the equation like this. So this is nothing, if this is equation number 1, we are getting equation number 1.1 here. Just we are changing u with u0. Okay. Now what we will do, we will subtract equation this from equation 5.1. That means you now subtract 1.1 minus 1. So you just subtract this equation from this one. Okay, so what it will happen, so it will create u minus u0, right? U minus u0, that kind of terms will come, and that will give you this equation. Okay. Okay, just hold on 1 minute. Am I audible? Hello? Hello?
Yes.
Okay.
Yes, sir.
Okay.
Yes,
So
sir.
okay, fine. So you see now what we are doing, we are just taking the main equation in form of u, and we are taking the equation with estimated value and we are subtracting them, and that if you do some little adjustment, rearrangement, you will get this equation. Okay, so where all these u0 and u dot term will be there. Okay, basically we are in this, from this expression we are removing this u part and we are invoking this u0 and u dot. So by subtraction we are expressing this equation in this form. Okay, now from this equation uh, there is a beautiful step, beautiful assumption we can take. We can take means Patankar, you know that Patankar is one of the very stalwart figure in CFD. He has a book and he proposed that simple algorithm, Patankar and Spalding. Okay, so that is a 1980 paper, scientific paper. So that has proposed this thing. So after deriving, Patankar take a very great assumption. The assumption is that this big equation you can write in this way. Okay, so in this way. So what it's showing, basically you are keeping this term and this term. and rest of the part all you are neglecting. All these things you are neglecting. Okay. So subtract, subtract this thing, and you can use these two equations, and you are finally getting this part, and then you neglect all these terms, only you are keeping this term, this equal to this. This is what? This is del t of the velocity correction, which can be equated to del x of pressure correction. You just u dot and p dot are the correction term. So the equation, he is assuming that this equation can be del u del t equal to minus 1 by rho del p dot del x. Okay, so this part will only sustain where only velocity correction and pressure correction terms will be there. Okay, so this is an assumption that assumption or approximation that was taken. And similarly, this is for x component velocity, u velocity only. If you do the same treatment for y component velocity, that is the y component of Navier-Stokes equation, then you will get this term. This is similar term. Okay. Now, question, there may be question whether this approximation is, or dropping of these terms is justified or not. Okay, so that is the big question, that whether you can do it or not. Okay, so here some lines are quoted from that very famous paper of Patankar in 1980s. So he says that yes, this can be justified. He says it is affirmative. So in the words of Patankar, who is one of the authors of simple algorithm, the argument goes as follows. So these lines are directly quoted from that scientific paper, from that famous paper. So let me read it out, then I will discuss it later. It will be clear. So it states that if they were retained, means if the other terms can be retained, they would have to be expressed in terms of pressure corrections and velocity corrections at the neighboring and the surrounding grid points. Okay, so if you keep all these terms, you see that you have u dot and u dot this u dot etc. and that correction, these velocity corrections, you need to consider in the other dx, means other the moment you discretize this dx, you need to calculate this velocity correction at the neighboring point, and when you go to that neighboring point, again it will call another set of neighboring cells where also do it. Ultimately, the whole domain you need to consider for the pressure correction or for this velocity correction, which is a cumbersome job. Okay, so that's why it states that if they were retained, they would have to be expressed in terms of pressure corrections and velocity corrections at the neighboring and surrounding grid points. These neighbors would in turn bring their neighbors and so on. Ultimately, the velocity correction formula would involve the pressure correction at all grid points in the calculation domain, and the resulting pressure correction equation becomes unmanageable. So if you do need to do the corrections for a particular point and you need to consider all the points of the entire set, then it is a very difficult job. Computationally it may be very difficult. The omission of any term would, of course, be unacceptable if it means that the ultimate solution would not be true solution of the discretized form of the momentum and continuity equation. Okay, so this omission, if after doing this approximation, if you see that whatever result you are getting, that is not the exact solution of the differential equation, then it is not acceptable. But actually, means surprisingly, the true thing is that even after neglecting that, whatever result you will get will basically satisfy the equation. So will be very close to the differential equation. So that's what it is said. The omission of any term would of course be unacceptable if it means that the ultimate solution would not be true solution of the discretized form of the momentum and continuity equation. It so happens that the converged solution given by simple, and this approximation is basically simple algorithm, all about the simple algorithm. So given by simple does not contain any error resulting from this omission. So even if you neglect it, it was found that the result is not being hampered. So in the converged solution, we acquire a pressure field such that the corresponding velocity field does satisfy the continuity equation. Okay, so after even after doing that, if you solve only these equations, so you will see that it will satisfy the continuity equation. The word semi-implicit in the name simple has been used to acknowledge this omission. Okay, so it is not implicit, it is semi-implicit because you are you are omitting these terms. These terms represent an indirect or implicit influence of pressure correction on velocity. Pressure correction at nearby locations can alter the neighboring velocities and thus cause a velocity correction at a point under consideration, and we do not conclude this influence and thus work with a scheme that is only partially and not totally implicit. Okay, so this is what up to this the Patankar's submission. Okay, so he has proposed this beautiful concept that even if you approximate the equation in the simple form, the result will not going to change. It's not going to change. Okay, so that is already proven, and he has shown it. Okay, so there, that is the crux of this simple method, that this entire equation you can transform in the form of only this simple form of del u del t equals to minus del p del x. So again, the velocity correction can be assumed to be 0 at the previous iteration step, and equation and both these equations, these two equations, this equation and these equations can be written in this particular form if you just consider a finite time step. So ultimately the equation was in proper form was like this, equal to 1 by rho minus 1 by rho del p del x. Now you can simplify it. If you consider a finite time step, instead of this delta t you can write delta t, and you can if you write it u dot in a finite form, u dot will be equal to minus a del p del x, where minus a is equal to delta t by rho. Okay, so this is one part, and similarly you can do for the v component. So v dot equal to a into del p dot minus rho. Now again, as a from the very first definition, we know that we have defined the exact velocity u equal to estimated velocity plus correction term u0 plus u dot. So we can write u dot as u0. So from here also you can write u equal to u0 minus, instead of u dot we can write this minus a del p del x. Okay, so this is one we write. So that is shown here, u equal to u0 minus a del p del x. So this is just from the definition of this. Similarly, we can get for v term this one, v0 minus a into del p del x. Now you put this u and v, expression of u and v in the main equation, main Navier-Stokes equation. So if you now you put this value of u and v in the continuity equation. Okay, so continuity equation is what? Del u del x plus del v del y equal to 0. So this is continuity equation. Now instead of u you write this one, and instead of v you write this one. Okay, so if you put all those values, then you will see that finally your equation is coming like this: del u0 del x plus del v0 del y minus a into del 2 p dot del x square plus del 2 p dot del y square equal to 0. And this, if you take in both hand sides, then it will be in vectorial representation, it can be shown as del square p dot will be equal to 1 minus a into del dot v0. So this is v0 is the estimated velocity vector. You know, v0 is v0 stands for the estimated value, and this is known as pressure correction equation. Okay, pressure correction equation, or sometimes it is called Poisson's equation. Okay, so in the solution of Navier-Stokes equation, we do not directly solve the continuity equation. Rather, we put the values of u and v in the continuity equation from this correction term based on simple algorithm. If you put this estimated correction value, so this equation will get. So this pressure correction term we will try to solve. Okay, so what are the three equations that we need to solve? We need to take the two in x 2D equations. We need to take two x component Navier-Stokes equation and y component Navier-Stokes equations, and we need to solve this one also. Okay, this pressure correction case. So if the estimated value velocity is correct, then it satisfies the continuity equation at every point, and the pressure correction is 0 at every point. So if your estimated value, whatever value you are estimating or calculating u, v, etc., if those are correct, then this part will be 0. This pressure correction will be 0. So if it is 0, then that is your result. If it do not belongs to 0, then you need to iterate again and again, step by step you need to move until and unless this correction term becomes 0. Whether correction term 0 means p is what? P dot plus p0. Okay, so p0. So p0 is the estimated value. So if your estimation is correct, it will be satisfied. Pressure correction will be 0. When pressure correction will be 0, so your estimated this will be 0, then this p will be equal to p0. So that will be the acceptable solution. So what is the logic? So you take the domain part, consider the staggered gauge arrangement, save the velocity at the cell face, and at the center you the pressure. You assume one set of pressure value, and based on that you find out the u and v here. Now after calculating this u and v at the cell face, you bring them or via interpolation to this point, to this cell center. Okay, so you bring them and you see that whether this pressure correction is satisfied or not. If it is satisfied, then it is acceptable. Otherwise, you change the value of pressure. So that is how pressure and velocities are coming up. So this is the theory. Now let us see that what are the steps. But before that, we will see that how using simple algorithm we can see the discretized form of the equation. That means the staggered gauge arrangement of the equation. This is the staggered gauge arrangement. I have already shown that in at the cell center, this is cell center ij. Here you will save the pressure value, and for this particular point, this is the velocity. U will be stored here at ui plus half j. This is I plus half. This is I plus 1. This point is I plus 1. This is at this I plus half position. I will store the u, and for the v component we will consider this one this one. Okay, so this is the v component. So it will be staggered grid. So the value related to this is one set of value. Okay, so u here, v here, and p here. This is the staggered grid arrangement, and in this particular, and the position of the face is denoted by I plus half comma j or ij plus half. Okay, so where this u and v will be stored. So in this particular arrangement, if I write the x component equation at a particular point mn, okay, at p plus 1, okay, so p plus 1 is this superscript, it indicates the time step. So p plus 1th step, if I write the equation, this will be the case in the form of estimated value del E0 del t at mn at p plus 1 interval plus the convective part. These two are convective part, then pressure part, and this is diffusive part. All are written at that point mn, and for the mn cell, actually for the mn cell, and at p plus 1 interval. Now you do the discretization. So how to discretization? If you use the explicit scheme, so for the temporal part we will consider explicit scheme p plus 1 minus p by delta t, that we have seen in the last class. So we have shown you step by step how this temporal term can be discretized, then how this convective term can be discretized, that we have shown here. Okay, so this is the convective term. Then this pressure term can be done in this way, and you see that all we are writing with the p0 in the form of p0, that is the estimated value. Estimated value means initial. So when you start the simulation, you will see that there is a initialization state. So you are initialized with some value. So with those values are taken right now, and you can consider this also. This is the diffusive part. So this is how you can discretize it. So similarly, the y momentum equation can also be discretized. This is y momentum, and this is the discretized form. So from the differential, you are coming to the algebraic form. So these 5.51 and 5.52 equations are basically the discretized momentum equations based on staggered grid arrangement. And the third equation that we need to solve is in the form of pressure correction equation. As I told you, we will not solve the continuity equation directly, but indirectly in the form of pressure correction equation. So that how this pressure correction equation is coming, we have already seen. So this we need to also solve at I, j and p plus 1 value. Okay, because those who are m and n, you note that this is mn position is different than ij position. Okay, ij position is basically the center position. Okay, so this I here it is I center, and mn is basically denoting I this phase and this phase. Okay, where your velocity will be stored. So you write it ij here and at p plus 1 interval again. So if you write discretize it again using central difference thing, this will be the discretized form. So these three set of equations you need to solve. Okay, so equation 5.1, discretized form of x momentum, discretized form of y momentum, and the pressure correction term. So these three equations you need to these are the linear set of algebraic equations you need to solve at each step. Okay, now you have to apply the proper boundary condition. As you know that boundary condition is important, so you can apply no slip boundary condition at the wall and no flow normal to the wall. Then Dirichlet condition in the at inlet, Dirichlet condition in the outlet, Neumann condition at the outlet. So these are different variety of boundary condition. We have also already explained all these things, right? That how to give the boundary condition. Now this is important, that how to put the boundary condition for pressure correction equation. Okay, because we know that boundary condition for momentum and on continuity equation, but here we will not solve continuity equation directly, but in the form of pressure correction equation. So if the velocity is specified, then del p dot del n equals to 0. This arises from putting u dot equal to 0, v dot equal to 0 in that equation, and if pressure is specified, then p dot equal to 0. Okay, so if the velocity is specified, then we can take this boundary condition that your pressure gradient is 0, or you can consider the Dirichlet type of boundary condition where p dot equal to 0. Now, if the outflow boundary condition, if at outflow boundary condition the flow is fully developed, then this is the case. The above boundary condition arises from the fact that the fully developed flow, in case of fully developed flow, del u del x equal to 0. So this is the case. So this will be equal to 0. Okay, so these will be the boundary conditions for the pressure correction equation. But again, this equation specific. It depends on the particular case, particular geometry. You have to take a proper boundary condition. Anyway, let us go to the simple algorithmic step. Okay, so that is much more important. So your equations are clear, I hope. You need to take the discretized form of x momentum, y momentum, and the pressure correction equation. So what will be the step 1? The step 1 will be initialize u and v at the staggered grid points. Okay, so you get some initialized value at of u and v at the staggered grid points, and guess pressure P0 at regular grid point, that is Ij. So u and v you take at I plus half and j plus half position, and pressure value at Ij position you take a guess. So this means u0, v0 and p0. Okay. Then locally linearize the convection terms of equation 5.51 and 5.52 and solve momentum equations at t plus delta t. So discretized form or linearized discretized form we have already seen, we have already got it, and now we will try to get the value. So this is at t, at time t equal to t, we are guessing, taking the guess of all these values. Now we need to find out the values at t plus delta t to find out u0, v0 at I plus half, I minus half, j plus half, j minus half, as shown in the figure. Okay, so that phase value we need to find out at t plus delta t. Now, so this is the solution of the momentum equation. Now you solve pressure correction equation to find p dot at ij, ij minus 1, ij plus 1, I plus 1j, I minus. So all the surrounding points you get the P dot pressure correction value. Okay, so if I consider only one cell here, so this is ij point, and you after initialize, you try to get the value of the u and v at these 2 points, these at these points at t plus delta t, and then you find out the p pressure correction term at this this point, in the surrounding cells. These are the surrounding cells. So all these surrounding cells you find out the pressure correction term. Okay, so if I mark them with cross, so at these cross points you need to find out the pressure correction term. Okay, not here, here. So these surrounding points. Then transfer U0 and V0 to pressure grid points Ij by interpolation. So that's why this interpolation scheme is required that we were talking about in the last class. Okay, because you have calculated the value at these points, at these phase points. Now we will check, because my pressure and velocity are different points. Okay, but that is our theoretical assumption, but actually at a particular point pressure is there, velocity is also there. Now we need to check whether whatever velocity we have calculated, that can satisfy the pressure or not. So that's why we will interpolate the velocity that is calculated at the phase to the center point. So you bring them at the center, then you correct the pressure and velocity using at the regular grid points, by using p equal to p0 plus p dot, and u equal to these corrections and v equal to these corrections. So now you need to this is the step where the pressure velocity is being coupled. So initially, based on the initial assumptions, you are getting this calculated value here. Now you bring them at the center and you try to couple this pressure and velocity. Okay, so using the definition of the pressure correction. Note that the corrections of U, V and P are implemented at the regular grid points. Now this correction is taking place at Ij, not at the cell center. Okay, have been derived at the regular grid point. Now replace the intermediate values P0, U0, V0 that we have initialized by the new corrected values of P, U, V. So after solving these two equations, these three equations, this P equal to P0 plus P dot, U equal to this one, V equal to this one. So you now replace that estimated value which we took earlier, you just change it with this new value and return to step 2. Then you again go to the step 2. And this loop you continue. Okay, from 2 to 6 this loop will continue until and unless your pressure correction satisfied the continuity equation. Okay, that means your pressure and velocity coupling is properly taking place. So at each step you need to move through this iteration. Then repeat steps 2 to 6 till convergence, and until all corrections becomes negligibly small. So when you will see that these correction terms p dot or u dot or v dot is very small, beyond a tolerance value of very small. Okay, so that you have to declare 10 to the minus 6, 10 to the minus 8, etc. in that order. So then you can come out from that loop, then go to the next time step and repeat the cycle till steady state is reached. Okay, so this is for each time step. So for moving from t to delta t plus delta t, you need to move through this steps 2 to 6 a number of times until and unless this p dot, u dot and v dot, this correction term becomes very small. So when this becomes very small, that means your calculated value is almost equal to your estimated value. Then you can go to again the next time step. Okay, and that's how step by step the simulation will go on. So this is the main part of pressure velocity coupling. So you calculate the value of the estimated value at the cell faces, then bring them to the center, check find out this correction term. Okay, check whether it is satisfying the pressure correction, and then again you move back you do for a number of times, then correct it and you move forward for the next time. Okay, so this is all about the simple algorithm. Okay, So I am not sure because this is the difficulty of online mode. I cannot understand whether you are getting it properly or not. But I tried to convey you the most important aspect of pressure velocity coupling in the form of simple algorithm. You can go to this book, the page, the snapshot of the book that I am showing you. You can get it in this book, computational fluid dynamics and heat transfer. This is a very good book for the beginners, although it has only covered the finite difference method, not the finite volume part, but basic concepts you can be very clear from this book. Otherwise there is no doubt of CFD books, huge many authors have written. So one of the fundamental books is Patanka's book, which is very famous. So you can take any book and study them to understand step by step. So for those who are new and mostly undergraduate students may find little bit difficulty, but don't get worried. Okay, so don't get worried. Uh, if you spend some time, there are many people we know that who are working on CFD but do not have idea about all these things. Okay, they can blindly work on that then. But a little bit of knowledge of this mathematical background, these are the grammatical aspect of theory. If you know it, you can manage the software in most efficient manner. Okay, so before going further, I like to move back to the to the last to that chapter of ANSYS Fluent. Okay, so if you remember this, we have discussed probably in the second or third lecture. So what we did, we have shown you that how to start a problem in ANSYS Fluent. Okay, starting from ANSYS Fluent, then you go step by step, you construct the geometry. Okay, so these are the geometry construction part. These are the meshing part. I told you the steps, right? So after geometry formation, meshing is there, and then after meshing you set up the problem. So here you see that it is asking that the moment whether this is pressure based or axisymmetric or steady state or transient. Okay, and gravity is should be included or not. So everything options are given here. Then you set up the model you need to set up. We are selecting at the viscous laminar part, and then you are declaring the materials part, material properties, etc. So water, liquid, that thing you are defining, and then boundary condition we are specifying. And after boundary, here the solution method, whenever we are coming to the solution method, um, solution method, where that is one, sorry. Yes, this solution method page, whenever you are coming, you will be asked to give a pressure velocity scheme. Okay, pressure velocity coupling scheme that you need to provide. If you push this drop down menu, a number of options will come. However, the most popular one is this simple algorithm, and it is the by default option. And you can also see that the interpolation scheme like second order upwind or some other Presto scheme, linear scheme. So there are so many options are available, so you can take the proper one. And rest of the thing is the monitoring part. Okay, how can you monitor the simulation? So this is how things can move on. So I just wanted to show you that uh, where this simple algorithm lies. Okay, I am not being able to close this. Just a minute. Okay. Okay, so let me come back to this slide once more. I am online, right? Please respond someone.
Yes, sir.
Okay, okay, okay. So this is all about. So once more, I like to just show you that how this pressure velocity coupling is taking place. These are the important part of Navier-Stokes equation. So main problem we face due to nonlinearity and pressure gradient. Okay, so these are the main things. Then we discuss little bit of staggered grid arrangement, because if you store all the variable at the same point, variables at the same point, then what may be the problems that we try to discuss. And after that, the solution is using staggered grid arrangement like this, and based on that simple algorithm. So how to do this? So you just break the pressure part into two things: estimated value and correction value. Okay, now you put those in the Navier-Stokes equations, and you can get these big equations if you write them and subtract them. But Patankar has take a beautiful assumption or approximations here. He just kept only these two parts, this part and this part. Rest of the things they have neglected, and they have seen that even after doing this, there is no problem as such. Okay, the results are almost same. Then they have expressed this in terms of this pressure correction term. They have defined U and V, and these U and V they have fitted in the continuity equations, and by doing that you are getting the pressure correction equation or Poisson equation, which is the equation which you need to solve. Okay, and which will give you the essence of pressure velocity coupling, because you see here pressure correction term is there and estimated values of velocities are there. So you discretize it in staggered grid arrangement. So these are the two-dimensional discretized form of Navier-Stokes equation for each point at a p plus 1 time interval, and this is the discretized form of the pressure equation. So you now apply proper boundary conditions, and then you follow these steps. So for each time step, you have to move from 2 to 6. From this step 2 to 6, 2 to 6 will give you the pressure velocity coupling, the correction. Okay. Then once it is done, you can move forward go for the next time step. Okay, so this is the essence of simple algorithm, and you can read this book. I just quickly show you that how this simple algorithm can be posed in the form of a control volume algorithm, because the equation that we are showing is basically finite difference approximation. So again, you can write it here, and this will be the Navier-Stokes equations in discretized form. So you can write it in this particular format. In here we are using non-dimensional form, so that you can do. I just going through the detail because there is no scope of step by step explain these things, but you can have a look. So these are the discretized form of the equations. Now you put the values, then you follow the steps. So this will be the final equation, which you step by step. That 2 to 6 part that we are discussing is again shown here in this control volume formality. So this is the pressure correction part, so that you are doing. Now there are some line by line diagonal matrix algorithms are there, so that you can use for that. So there is another method like simple. There is another popular method by map, marker and cell approach. So which was also shown here in the help of three-dimensional geometry. Okay, so this is shown that how all these terms can be discretized. So discretized quotients are there, then the entire equation how you can move, it is shown here. Finally, this pressure correction is being taking place, and this shows the implementation of boundary conditions etc. in the 3D geometry. And these are some numerical stability criteria, CFL criteria, and another von Neumann stability criteria. So there are many methods to check the stability. So I am not moving into the going through the details of those things, but uh, let me tell you that this is the mathematical background of CFD. And if you like to do some research project or some project to learn, means main way to learn CFD is to do some project. Okay, so only reading and only thing is not going to work. So there is a saying like the taste of the pudding lies when it is tasted. Okay, so it is like that. So if you only work on it, you can understand this concept. And the more time you spend, the more concepts will be clear to you. And some of the problems where challenge lies, where research needs attention, where you can do good projects are like this. Multi-phase flow modeling, that's an important aspect. Turbulence modeling is another important aspect. Phase change is another important part. I have not covered anything, any bit of it. What I covered in this short course is basically how you can solve a single phase momentum equation. Okay, so phase change, turbulence, these are not untouched yet because it is a broad course. It needs sufficient time. Then reactor modeling for the chemical engineers, this is an important part. Multi-physics means you couple other equations. For example, you can apply electric field in a fluid flow. You can apply a magnetic field in a fluid flow. Okay, and you can see the effect in it. So these are some multi-physics, means different kind of physics you can apply on this with this fluid flow. So those are also challenged. So specifically, if you are using COMSOL multiphysics, then you will get these options easily, and many more other things are there. I am just putting only few things. Okay, so where you can do the things. If I like to have look back this sixth class that I have taken with you is first we started with introduction to CFD and its need and applications and why you should learn it, what to learn, what are the prerequisites. Then we move to the governing equations, Navier-Stokes equations and its complexity, what are the needed and what are the steps to solve them, that we have discussed. Then various elements of CFD solver we have discussed, like discretization, numerical error, stability, different type of grids, okay, different discretization schemes. Okay, so that thing is clear. Then solution method of PDEs from one-dimensional heat conduction to Navier-Stokes equation. This part I have covered mostly mathematically, and introduction to anti-student along with some tutorials. So these things I have covered, and remember this is only just the ABCD. So I started with the topic called ABCD of CFD. Okay, so it is only an ABCD. So if you like to write an essay, you need to spend time on it. However, this is an interesting area which can solve many practical problems, many natural problems, many understanding purpose. Okay, if you like to understand physics of fluid flow at different conditions, then this is an excellent platform, I would say. Many groups worldwide work on it. Okay, so you find work on it, and if you can learn it, then you can venture into many directions. Okay, so that possibility is always there. So mainly I what I find is mostly undergraduate students are attending this workshop. So I tried to give all of you a little bit of idea about CFD. If you attend these things, the last today's class will be little bit difficult for you, most of you, to understand, to digest actually. So I know that, but if you stay with these things, you spend some time, gradually you will see that the entire picture will be clear to you. It is not, nobody can understand this thing at one go. Okay, this is the aspects of simple algorithm. It is very difficult to understand at a single go, but you can definitely read something, you can work on it, picture will be clear. Okay, so with this I am at the very end of this workshop. Now I will be ready to take some questions from you. So please feel free to ask any kind of questions that is in your mind.
Hello, sir.
Sir, what was
Yes, please.
Please, sir, can you go back in slide at the
Uh,
beginning of the simpler where you are canceling those terms?
yes, please, just 1 minute. Please give me 1 minute. Yes. I think you are talking about this one. This one. Yes, this slide you are referring.
Yes, sir. Yes. Why? Why? Can you, sir, please explain once more?
So this is part. Look, up to arriving this point is not a problem. Okay, so all of you can understand these things. Okay, no difficulty it is. But here, if you like to solve this thing, this entire equation, okay, if you like to solve this entire equation, there is some problem. The problem is that you have to consider u dot at all the grid points. So you see that once you like to do the correction, you need to consider the velocity of the neighboring point. Then if you like to consider the velocity of the neighboring points, that will uh, uh, again need the invoking of the neighboring cell of it. Okay, so finally for each cell, for doing this correction, you need to consider the entire geometry. The entire geometry means what? Let's say in normal simulation, you can take 1 lakh grid or grid points. That is a very small scale I am talking you. So if you have 1 lakh points, and for each correction, each pressure velocity correction, if you need to take 1 lakh correction, means 1 lakh points to solve. So it will be a huge business. So your simulation will be very slow. Computationally, it will be very difficult. Okay, so what this assumption is doing, that they are neglecting all other terms. Okay, so all these other terms they are neglecting except these two parts. Okay, and even after retaining only these two terms, it was found that the solution is not going to change too much. That means the effect of these all these terms are uh, not so very high, because that is if you practically think that if you have a very big domain, okay, so your uh, I'm just doing some rough sketch. So let's say you are considering this cell. Okay, so you are doing the correction on this particular cell. Now, the effect of the velocity correction on this particular cell will have a very little influence which on a or of a cell which is far away, located far away. Okay, so this cell velocity and pressure will be mostly guided by the surrounding neighboring only. So the cells which are far away will not have very strong influence on this. So this is not required at all physically if you think. So if you consider only the surrounding cells, this is good enough. This is physical. Now that's why even if you neglect this approximation, it was found that the correction that you are obtaining from or retaining only these two terms also, the final result is not going to change too much. Okay, so this is a uh, very good assumption, I would say, means, and they have proved it. Now, how mathematically it is happening, if you like to understand, you can do more analysis, a detailed analysis on it, and the analysis can reveal you that the things. But this works in a number of cases. They have shown it, and it is well accepted. It is found that this approximation is quite good. Okay, so that is the beauty of this algorithm. It is not I am doing, it is already reported and proved things. Is it clear, or if you have any other doubt?
Yes, sir. I get it. Thank you.
Okay. Okay, it's a good question. Indicates that you are following. Any more questions?
Sir,
Yes.
in pressure velocity
Hmm.
problem using simple algorithm, when
Hmm.
will be able to know that my problem has reached to a solution by
Hmm.
seeing in the software fluent? And second question is where we can find the pressure versus velocity data in the software after running the problem.
No, collection of data is not a problem. In ANSYS 12, you have options. Okay, so whenever there is a monitor section where you are giving that what are the data that you like to see. Okay, so if you mention that, at each stage it will show you the pressure, velocity, etc. So you will see that some graphs are moving on, okay, going up and down, so that online you can move, you can see during the running of the simulation, you can see. And the first question you are asking, that when to know that your things are actually, when correction term is the pressure correction and velocity correction that we are doing. So if that satisfies the continuity equation, so how to know that? If the correction terms becomes 0, so what is our, we are assuming that your velocity u will be equal to estimated velocity u0 plus u dot. So if u dot is the correction term, right? So when correction term 0, u dot goes to 0, then u equal to u0. So you are basically reaching the solution.
Okay. Thank you, sir.
Okay. Any other question? Okay, I think it is given is okay. So I again suggest you that all of you have some practice. ANSYS student is freely available, student version, so you can practice it, you can learn little bit, explore it, and then once you have interest, you can go for OpenFOAM also. OpenFOAM is a free software, so that can be tested, but definitely at a higher level if you have some interest. And in BTech level, I don't think how much time you can devote, because it needs a time consuming thing. If you need to devote time for understanding all these things. Okay, so if there is no more questions, I would stop here. And as usual, these last two class recordings I will upload and share with you in the WhatsApp group. If you are interested, you can revisit at any portion, and if you have any queries, you can write me. Or if you are, yes.
Hello.
Yes.
So for CFD simulations, I think you said that after we do the simulation in the software, we have to actually test with the actual data from the experiment that is coming, right? So it will be very helpful if you can share one real-life experimental data of a project, and then if we do a simulation on the software, we can like test whether we are doing it correctly or not.
This is a very good. I was talking to one of our BTech students in our lab regarding this. Look, all of you have some UG lab, right? Heat transfer or fluid mechanics lab. Okay, so the best way I suggest you. So, and there you have done some experiment on heat transfer and fluid mechanics, either pressure drop calculation or heat exchanger thing that you have done, right? So I suggest you take one of the experiment, any simple experiment, let's say one heat exchanger experiment that you have done. Now the experimental data is with you. You know that in case of heat exchanger, let's say it is a cell and tube heat exchanger with 1-2 parts. So then you know the geometry from your experiment manual. So you draw that geometry in ANSYS Fluid. Okay, and they make it 2D itself. And you know that at what flow rate you have passed the fluid and what temperature, that data are with you. You're supposed to have those data. And if you are interested, you can go back to your UG lab and conduct the experiment once more sincerely. Take the proper data, proper temperature, flow rate, etc. And then you try to simulate it and see it is matching your results or not. Okay, so that is the best way to do it. Otherwise, if you go to the scientific literature, there are huge number of papers are available. You choose any one and you can try to validate the results, whether the same result you are getting or not. Okay, that is also possible. But simplest way is to do that. You have the experimental data in your hand from your fluid mechanics or heat transfer lab. Choose one of them which is little bit simple geometry, and then try to simulate it. Okay, and see whether your results are matching or not. That is the best way.
Thank you.
Ah,
Can
okay,
you
yes.
please share copies of
Yes.
CFD? You share some CFD books because we don't have that much material. CFD regarding CFD.
So, who are talking you? Are you NIT Durgapur student or outside?
Yes, sir, I'm from NIT. I am from mechanical.
A mechanical from NIT, right?
Yes, sir.
And then you need not worry about it. You go to our library. There is no
Okay,
dearth
sir.
of books. Or even if you in your Google you search it, CFD free available. Maybe you will not get books, but there are huge materials available. Either presentations or PDF files, whatever you will ask, some you will get. Okay. All of them are not of equal quality, but sufficient material you will get. And if you go to our library, there is a very good collection of books on this topic, on computational fluid dynamics.
Okay, sir.
Look, nowadays there is now no dearth of resources. In fact, there was a time when teachers were there to help you find out the resources, right? Books, notes, etc. But now teachers' role is a little different. That how we can protect you from the huge collection of the data. Which will be the most suitable one. So choosing that is the challenging task for us. Okay, so there is no doubt of it. That's why I pointed out only one book for the beginners. Okay, that goes to that book, because there is big books, big celebrated authors have a lot of books, but this book has, if you are a beginner, it will help you. I can tell you, you can read yourself and you can understand the things. Okay, then you start working, you can take it up.
Sir, can you tell me again this book name?
Is P.S. Ghoshkostidar book. Okay, you are in the WhatsApp group, I will share that PDF file of that book. Okay, along with the details, publisher, etc.
If it's possible to share the PDF of this book.
No, PDF is not available. That's why I am struggling. I was just trying to scan it and showing it to you. If PDF was available, I could prepare my slides in a better way. PDF of this book is not available.
Sir, library have not much more books. That's why I'll tell sir.
Much more? What?
Actually, sir.
Sir, library have not this book, sir.
This book you may not be a library, may not have, because this is not so. I would say that you do. This is a very low cost book, very thin book, a very small book. This one. This was basically written on the class notes of a professor. Okay, and it is costing more than 200 or 300 rupees maximum cost will be. So if you may not
Yes.
get it in library, but you can buy it online. 200-300.
Yes, sir. In Amazon, but there was no, it is not available. Actually, it is
PDF.
showing that the not available, but no, not sir, not the PDF. The hard copy of the book I searched in Amazon. The goes to there.
The hard copy was
Paperback.
available. I looked into back a few days back also, it is available. You search Flipkart, etc. You get.
Flipkart.
Sir, we have learned about the simple algorithm. So there are also other solvers that are present, like simple C or simple R, then
Simple
Mac.
R, Mac,
Yeah.
many things.
So, sir,
Many things.
can you say me like when to use simple R or when to use simple R and the other ones?
It will be the exact choice of the solver will come with experience. Okay, so if you are expert in CFD, you can from identifying the problem itself, you can understand that which one to choose for which case. Simpler is general, you can apply. Simple is used anywhere in general, but to choose the most appropriate solver for the particular problem comes from the experience, or if you are a beginner, you have to do some literature survey. Okay, you suppose you are doing some reactor flow problem, modeling problem. Okay, so you are simulating a reactor. or heat exchanger, whatever. Now you first step of doing a project or research is that you do some entire literature survey. That's why we put emphasis on it. Okay, most of the students become bored on it and they do not pay sincere effort on it. But you find out the papers, all the papers whichever have been reported on particular that kind of problem. Then you see that what most of the researchers have done. Okay, so once that is done, then you means that is done, you find out the most suitable algorithm and imply it. Okay, that's what we suggest to our scholars. Okay, so you find out the which method is adopted by most of the researchers, then you select that. Okay.
Yes.
Okay, then thank you very much for being and showing your interest in attending these weekend sessions, and I thank case members for giving me this opportunity to interact with you all. I am those who are NIT students can interact with me in this topic anytime if you wish, and that's all. Thank you very much. So let us close now. Uh, so let us now stop. Okay, thank you.
Sir, you tell the version of the ANSYS software that you showed in the PDF. I downloaded one version from it, but the workbench is something different, like a little bit different.
Look, there are so
Can you-
many versions available. Okay, so even each year they release 2 new versions. Okay, so
Yes, sir.
the version to versions it may change, but don't worry about that. The basic structure of the CFD things algorithm will be remaining same. Okay, there may be little bit change in the interface, but don't worry about that. You will find all the options in different color in different positions. Okay, the basic structure algorithm is same. That is not changing. Interface is changing. Okay. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you, sir.
Thank you. Thank you.